All right, so in this video, we're going to take one last look at a related rate problem. This will be number 30 on page 160. It's a little more theoretical, but the process won't be any different. And so we're supposing a drop of mist is in a perfect sphere, and that through condensation, the drop picks up moisture at a rate proportional to its surface area. Show that under these conditions, the drop's radius increases at a constant rate. So this, again, I'm not going to write a need and know column. It's all just going to kind of be laying out the groundwork, and then the result happens. But it's really a matter of taking the problem given in words and translating it into our calculus notation. So the first thing I know that I'm going to acknowledge is that we're dealing with a sphere. And the volume of a sphere is 4/3 pi r cubed. The other thing I'm going to acknowledge is that the surface area of a sphere is 4 pi r squared. Now, it's saying in the problem, the drop picks up moisture at a rate proportional to its surface area. So a rate, that's going to be your derivative, and that's our volume changing in this case. If it picks up moisture, our volume is going to be changing, so the change of volume with respect to time is going to be proportional to its surface area. All right, so now from here, I'm going to make a simple substitution. I know that my surface area is going to be 4 pi r squared. So I've got my k times 4 pi r squared, which you could clean up if you really wanted to a 4 pi k r squared. Okay, so again, nothing really crazy that's been done here. I've made a couple acknowledgments that that's the volume, that's the surface area. This is a fact that they're telling us. The change in volume with respect to time is going to be proportional to its surface area. And then by making the substitution, I end up with dv dt equals this. Well, now let's actually work it out. If I take this and I dt it, that's going to give me a dv dt result. So the change of volume with respect to time, if I take this now with respect to time, this is going to give me a 4 pi r squared dr dt. But now this result should equal this result. So if I come down here now and I set both of those things equal to each other, 4 pi r squared dr dt has to equal 4 pi k r squared, then 4 pi's go away, the r squareds go away, and we find out that our dr dt is equal to k, which is a constant. And that's exactly what they wanted us to show. Show that under these circumstances, the drop's radius increases at a constant rate. So our change of radius with respect to time is equal to k, the constant. So again, as I promised, it's a matter of just kind of stating the facts, and then you'll see it kind of all fall apart into the end result. This is essentially more of a proof or a derivation than it is a problem that you need to solve for a specific number. But yeah, just another nice application of what related rates can do for you.